Simon is a free-floating artificial intelligence, and when he will be activated, this is kind of a historical moment. So we are very happy that Simon will be the first artificial intelligence in space. That for us, this is a piece of the future of human spaceflight. I mean, if you go out to the moon or to Mars, so you cannot take all mankind and engineers with you, but with an artificial intelligence, you have instantly all the knowledge of mankind.
If Alexander Gerst has certain questions to that experiment he's working on, Simon has quite deep knowledge on that experiment. So he can really get inside the experiment and he can ask questions that are beyond the procedure.
During the times when there is connectivity, all the communications go back through the cloud. So all the AI work is being processed at the cloud, natural language, all the training and tailoring we did happens in the cloud, which also means we can enhance it from the Earth anytime and make it smarter constantly to help Alexander and the team to use it.
We are studying chemical gardens and their inorganic precipitation structures that are looking extremely lifelike. Another motivation is to turn this into a new type of engineering. So on the left you see hydrothermal vents, these white and black smokers on the ocean floor. They're a possible place where life might have started on Earth. So the idea is here to essentially grow tubular structures in a more organic, lifelike way. So we believe that this is something that you also can do with inorganic materials reactions and turn this into a different type of technology.
And this is basically what they look like here. We have a burst bag here with a weak seal in the center. There's a Teflon insert with a wire on it to which we've attached the crystals. In the bottom is the sodium silicate solution. This will be put into the glove bag and it'll be rolled up. The seal will break and the solution will come in contact with the crystal, and we'll see what the growth is when it comes back.
The latching end effector is really, or the LEE, is the business end of the Canadarm2. So on the Canadarm2, we actually have one of these latching end effectors on each end of the arm. Now that allows us to grapple payloads, it allows us to capture vehicles. It also allows us to connect to different attachment points on the station, and it allows us to make a structural, power, data, and video connection there so that we can then effectively use the other end of the arm as the base. That allows the arm to be able to walk around the station. Now the trick is we want to launch this new latching end effector and put that on station to have an available spare. Because we do the assembly, the maintenance operations, because we do the resupply of the station with the space robotics, and it's a critical system, we always want to be able to protect for a failure. So if we get any kind of random failure or any kind of issue that pops up, we want to have that available spare on orbit and ready for us to swap that in if we need it.
We're going to send some sediment to the International Space Station. And what we're interested in is looking at what we call cohesive forces in sediment. These cohesive forces are very important to how sediment gets transported in the environment and in engineering systems. However, they're very weak if you compare them to the force of gravity. And that means that it can be very hard to study them accurately here on Earth. Whether sediment behaves cohesively is very important to the transport of any contaminants or pollutants that stick to the sediment. Here you have sediment settling under the effect of gravity with different degrees of strength for the cohesive forces. Of course, we can also turn off gravity and then mirror what we're going to get on the space station. And by comparing the simulations to the ISS experiments, we can then deduce models for how sediment gets transported, which then we can use for the benefit of life on Earth.
EcoStress stands for the Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station. It's actually a thermal infrared radiometer that measures the energy that's coming off the surface and then translates that energy into a temperature. That is where EcoStress is going to go. You can sort of see it's highlighted there on the left. And so what will happen is this video will zoom in and we're actually looking at Salton Sea, and you can see the green fields. This is what you'd see if you're looking with your eye, but EcoStress will see the temperature, and you can see the different areas, the blue, colder areas, and those are the areas that are being watered or being irrigated.
This is just a fantastic mission. It will help folks making real-time decisions in several areas. Water managers need to know where to use water, again, the minimal amount of water necessary in a time of increasing water scarcity. And also because it's a temperature sensor, it has temperature channels on it, it will help us understand some major natural hazards such as droughts and also hotspots from fires and volcanoes. And then finally, it's going to give us the big picture for all natural resource managers, terrestrial natural resource managers, to how their systems are doing, how their ecosystems are doing. Are they stressed or not? And for that, of course, it all starts and ends with the plants.